I am Shamsunisa from Royal Degree College Chemistry Department. As we have already started Unit 4th General Chemistry, so today we will talk about Chapter 4 Electronic Spectroscopy. In this we will study ultraviolet spectroscopy, types of electronic transitions, molar absorptivity and transition probability, AUXOCHROME, intensity shift, chromophore, absorption characteristics of chromophore, Woodward-FIESER rules to calculate lambda max for DIENES and ENONES, and Scott rule to calculate lambda max for aromatic compounds. First of all, we'll study about UV spectroscopy. Spectroscopy involves the interaction between the matter and radiation. UV spectra is also called electronic spectroscopy, since it involves the promotion of ground state electrons, that is sigma, pi and n, to the higher energy states. UV radiation with wavelength lambda equal to 2000 degree angstrom to 4000 degree angstrom, that is 200 nanometer to 400 nanometer, is used in the UV spectra. When a compound absorbs or interacts with the UV radiation, electronic transitions takes place in the molecule. That is, the electrons gets excited from bonding orbitals, ground state orbitals, to the anti-bonding orbitals, that is nothing but excited states. Now we'll see about types of electronic transitions. According to molecular orbital theory, when a molecule absorbs energy, that is UV radiation, its electrons are excited from bonding orbitals sigma, pi and n to anti-bonding orbitals pi star, sigma star. Here you can see the graph. On the x-axis we are taking electronic transition energies, and on the y-axis energy. You can see the states sigma, pi, n, pi star, sigma star. So the electronic transitions, actually they are of four types. They are, first one is sigma to sigma star transition. Second one is n to sigma star transition. Third one is pi to pi star transition, and the fourth one is n to pi star transition. So the energy required for these transitions is in the order sigma to sigma star, energy required is more compared to n to sigma star transition. N to sigma star transition requires more energy compared to pi star transition. Pi to pi star transition requires more energy compared to n to pi star transition. It means that n to pi star transition requires less energy and sigma to sigma star transition requires more energy. So we'll talk about first transition, that is sigma to sigma star transition. This is a high energy process due to large energy gap between sigma to sigma star orbitals. This transition is not observed in the normal UV region, that is 200 to 400 nanometer. Why? Because this transition occurs below 180 nanometer, that is in vacuum UV, and this transition leads to bond breakage. This transition is possible only in saturated compounds, that is nothing but alkanes. Second type of transition is n to sigma star transition. So these transitions takes place in saturated compounds with one heteroatom. It is observed in alkyl halide, alcohol, ether, amines, etc. This transition also requires high energy and occurs below 200 nanometer, but requires less energy than sigma to sigma star transition. Third type of transition is pi to pi star transition. These transitions takes place in unsaturated compounds like alkenes, alkynes and aromatic compounds. These transitions require less energy than first two and can be observed at larger wavelengths. Fourth type of transition is n to pi star transition. This is the lowest energetic transition among all electronic transitions and hence occur at longer wavelengths, that is above 200 nanometer. This transition can be observed in compounds with heteroatoms and unsaturation. where an electron of lone pair of heteroatom gets excited to pi star, that is antibonding orbital. This transition is best observed in carbonyl compounds, that is nothing but aldehydes and ketones. This transition is also observed in carboxylic acid, acid derivatives like amides, esters, acid halides, etc. Nitro compounds, cyanides, oximes, azo compounds, etc. Next is molar absorptivity. It is indicated with epsilon max and transition probability. What is this? The molar absorptivity is also known as the strength of absorption. It is defined as the proportionality constant which relates the absorbance A at lambda to the molar concentration C of the sample and the length L in centimeter of the path of light through the sample. Like this, we can write the formula for molar absorptivity, that is epsilon max, it is equal to absorbance into molecular weight into 100 divided by concentration of compound in milligrams per 100 ml into path length in centimeter. Depending on epsilon max value, the transitions are divided into two types. First is allowed transitions and second type is forbidden transitions. Now we'll see about allowed transitions. What are allowed transitions? The transition with epsilon max value more than 10 to the power 4 are usually called allowed transitions. So here epsilon max value is greater than 10,000, that is nothing but 10 to the power 4. They are allowed transitions. Generally, pi to pi star transitions are allowed transitions. Now, second type of transition is forbidden transitions. These transitions with epsilon max value less than 10 to the power 4 are called forbidden transitions. Generally, n to pi star transitions are forbidden transitions. Example, for benzophenone, the observed transitions are 252 nanometer at this epsilon max value, that is equal to 20,000. These are allowed transitions. And 325 nanometer epsilon max value equal to 180. These are forbidden transitions. AUXOCHROME. Now we'll talk about AUXOCHROME. A group which does not itself absorbs radiation independently, but its presence brings a shift in the absorption band towards the longer wavelengths, that is towards the red end, is called an AUXOCHROME. In other words, an AUXOCHROME is called color enhancing group. Example, OH, OR, NH2, that is amine, NHR, dialkyl amine, SH, etc. All these groups are considered to be as the AUXOCHROME. Example, another one we will see, that is benzene shows an absorption maximum at 255 nanometer. Epsilon max value equal to 203. Whereas aniline absorbs at 280 nanometer, where the epsilon max value equal to 1430. Hence, amino group, that is NH2, is an AUXOCHROME. Next, we will see about intensity shift. It is of two types. First one is bathochromic shift, which is nothing but red shift. And second type is hypsochromic shift, which is also named as blue shift. First of all, we'll talk about bathochromic shift, red shift. The shift of the absorption maximum, that is lambda max, towards longer wavelength. Why? Due to the presence of a group, AUXOCHROME, or a reagent that is nothing but solvent, is called bathochromic shift, or it is also termed as red shift. Example, phenol has the lambda max value equal to 260 nanometer, but phenol in sodium hydroxide solution absorbs at lambda max equal to 270 nanometer due to the formation of phenoxide ion. Here you can see the reaction. Phenol we are taking in sodium hydroxide solution. Okay, then we will get here pH single bond O minus, which is nothing but phenoxide ion. The lambda max value for this phenoxide ion will be equal to 270 nanometer. Next, second type we'll see, that is hypsochromic shift. That is nothing but blue shift. What is this? The shift of the absorption maximum, lambda max, towards shorter wavelength or due to the presence of a group or a reagent is called hypsochromic shift or blue shift. Example, aniline has lambda max value equal to 280 nanometer, but aniline in hydrochloric acid solution absorbs at lambda max equal to 250 nanometer. Why? Due to the formation of phenylenium ion, that is pH single bond NH3 plus ion. Here you can see the reaction. We are taking aniline. pH is the benzene ring to which NH2 is attached. That is named as aniline. Aniline we are taking in hydrochloric acid. Okay. Here the lambda max value for this aniline is 280 nanometer. From this we are getting a product as phenylenium ion. The lambda max value for the phenylenium ion is 250 nanometer. Next we will talk about chromophore. What is chromophore? It is an isolated covalently bonded group which is responsible to show a characteristic absorption in the ultraviolet visible region. Due to the presence of chromophore, compounds exhibit color. Hence, a chromophore was considered as any system which is responsible for impart color to the compound. Compounds with the same functional group will absorb the radiation of nearly the same wavelength. Example, NO2 group imparts yellow color to nitro compounds. N double bond N, that is the azo group, imparts color to azo dye. Other examples are C double bond C, C triple bond C, C double bond O, COOH, NO2, C triple bond N, and N double bond N, etc. All these are the examples of whom? All these are the examples of chromophores. Some of the chromophores, their absorption maxima, that is lambda max, extinction coefficient, epsilon max, and the types of transitions are given in this table. Here you can see the chromophore. The first chromophore is C double bond C. Lambda max value for this chromophore is 175 nanometer. Epsilon max value for this is minus 15,000. Types of transition here is pi to pi star transition. Second chromophore is C triple bond C. Lambda max value, the first lambda max value for this chromophore is 175 nanometer, for which epsilon max value is minus 10,000. Then the type of transition is pi to pi star. The second lambda max value for chromophore C triple bond C is 196 nanometer. Epsilon max value for this is 2000, and the type of transition is pi to pi star transition. The type of chromophore here is C double bond O. The lambda max value for this is 180 nanometer. If the 180 nanometer is the lambda max value for this chromophore, epsilon max value is 10,000. Types of transition is pi to pi star. Then for this C double bond O chromophore only, lambda max value, another lambda max value is 285 nanometer. For that, epsilon max value will be 15. Here the transition is N to pi star transition. Then fourth type of the chromophore, as we are seeing here, NO2, for which lambda max value is 274 nanometer. Epsilon max value is 15. Type of transition is N to pi star transition. Now we'll talk about absorption characteristics of chromophores. Woodward and FIESER formulated certain empirical rules for calculating the absorption maxima, that is lambda max, for dienes, enones, and aromatic chromophores. According to Woodward-FIESER rules, each type of diene, enone, and aromatic chromophores has a certain fixed basic value of absorption maxima, that is lambda max, which depends on the number of alkyl groups bonded, the number of double bonds with extended conjugation, and the presence of polar groups such as Cl, Br, Or, etc. So first of all, we'll see this one, that is Woodward-FIESER rule to calculate lambda max for dienes. This you have to remember here. Parent value of butadiene, that is acyclic conjugation diene, for that the parent value will be a constant value. All these are the constant values. These values you have to remember for the calculation of lambda max. Okay, for dienes. Here the value, the parent value of butadiene, if it is acyclic conjugation diene, so the value is 217 nanometer. Homoannular conjugation diene, for that the value will be 253 nanometer. Heteroannular conjugation diene, hetero means different rings are present in the diene, then the value we are taking as 215 nanometer. Alkyl substituent is there or ring residue is there, and the exocyclic double bond, chloro, bromo substituents are there. For each, the value we are using as plus 5 nanometer. Now here we have to calculate here we are seeing the problems. The first problem is calculate lambda max for 2,4 hexadiene. In the solution, you have to draw the structure of 2,4 hexadiene. We are writing the structure. CH3 single bond CH, double bond CH, single bond CH, double bond CH, single bond CH3. Okay. So here the basic value for this diene is, we are taking as 217 nanometer. Why? You can see here. Why we are taking 217? Because the parent of the butadiene, that is acyclic conjugation diene. Its value is acyclic, means it is not showing the ring structure, isn't it? So its value is, and the diene, the two double bonds are there. For that, the parent value is 217. So that's why we are writing here 217 nanometer. Okay. Then two alkyl substituents. Where? See here, one methyl here, this corner CH3, this is one alkyl, and this side another alkyl group. The two alkyl substituent. For each alkyl substituent, the value we are taking is plus 5. So 2 into 5 will get the value as 10 nanometer. Now we are adding these both values, 217 plus 10, you will get the lambda max value for 2,4 hexadiene is 227 nanometer. Okay. Next, we'll go to the next problem. Second problem, calculate lambda max for this particular compound. Okay. So here the basic value we are seeing, that is heteroannular. These are the ring compound, isn't it? And the hetero, different rings are there. Heteroannular. So for the heteroannular, basic value will be 215. Okay, nanometer. Then ring residue. Ring residue here, that is 4. How we are going to count the number from this side? This is the first position, second position, third position, and this is the fourth position. Okay. 4, and here also from this side next to the double bond we are counting the corners, that is the carbon atom. 1, 2, 3, 4. Okay, so the ring residue will be 4 into 5. Each value should be multiplied with 5. Okay, so the 4 into 5, so you will get the value as 20. We are adding both the values, so you will get 235 nanometer. That is the lambda max value for this particular compound. Next problem is calculate the lambda max for this compound. Okay, so the basic value, this is homoannular diene. Homo means same, one ring is there. Okay, homoannular diene, the two double bonds are there in that. For homoannular diene, the basic value, it is already mentioned. Those values you have to remember. 253 nanometer, that is the constant value we are writing. Then alkyl substituent plus ring residue. See, alkyl substituent. Here the alkyl substituent is how many? Alkyl substituents are 1. Okay, alkyl substituent is CH3 is the alkyl substituent. Okay, 1. And rest of the 2. Here next to the double bond, this is one carbon and this one, the 2 positions. So altogether how many alkyl substituent? 1, ring residue 2. So 3. Each value should be multiplied with 5. So 3 into 5, you will get the value as 15 nanometer. Now you are adding both, so you will get the value as 268 nanometer. That is the lambda max value for the organic compound. We have calculated. Next, we'll see Woodward-FIESER rule to calculate lambda max for enones. Okay, these values also you have to remember. Basic value of enone, that is enone means C double bond C, single bond C, double bond O, single bond X. If suppose here X is the alkyne, at that time you are going to write this basic value 215 nanometer. If X is hydrogen, In place of X, if hydrogen is there, so the basic value we are going to write it as 207 nanometer. For alkyl substituent, if the alkyl is substituted at alpha position, the value should be plus 10 nanometer. If alkyl substituent is at beta position, plus 12 nanometer. If alkyl substituent is at gamma or more positions, at that time the value should be written as plus 18 nanometer. Now we'll do the problem. The example is the first one is calculate lambda max for this particular compound. Okay, as we are taking this compound, here we are seeing this. Here, look at this. The basic value for this compound. It is the basic value for this compound is 215 nanometer. Why we are using the 215 nanometer? Because here CH3 is the alkyl group. You can see once here. If the alkyl group, X is the alkyl group, at that time the basic value we are writing what? 215 nanometer. So that's why we are writing here the basic value for this one is 215 nanometer. Then the two beta alkyl groups. Two beta alkyl groups here, look at this. Next to the carbonyl carbon, this carbon is alpha carbon. Next to this carbon, beta carbon. At the beta carbon, the two alkyl groups are present. These are the two alkyl groups. If the alkyl group is giving the value, constant value 12. So 2 into 12, you will get the value as 24 nanometer. Now we are adding both the values. Lambda max value will be equal to 239 nanometer. Next problem we'll see, calculate lambda max for this particular compound. So basic value here is how much? 215 nanometer. Why? Because here the alkyl substituent X, this is alkyl group. X, this alkyl group, X is equal to R, okay, alkyl group. So because of that reason, here we are taking the value, basic value as 250 nanometer. Beta substituent means this is the carbonyl carbon. Next to the carbonyl carbon is the alpha carbon. Next to that beta carbon. Beta alkyl group is present attached to that beta carbon. So one alkyl group is present. So we are adding plus 12. If you add both this 215 plus 12, you will get the lambda max value for that compound is 227 nanometer. Now we'll see about Scott rule to calculate lambda max for aromatic compounds. Like Woodward-FIESER rules, Scott derived a set of rules to calculate lambda max for acyl benzenes. So acyl benzene is nothing but PHCOX. Okay. Here the basic values. Again, you have to remember these values for doing the problem. If X is the alkyl group, at that time the value will be basic value 246 nanometer. If X is hydrogen or OH group, so basic value will be 250 nanometer. For alkyl substituent, if the alkyl substituent is at ortho or meta position, the value will be plus 3 nanometer. If the alkyl substituent attached at para position, the value will be plus 10 nanometer. Okay. Then if a halogen at para position, that is halogen, the chloro, if it is chloro, so the value will be plus 10 nanometer. If it is bromo, the value will be 15 nanometer. Okay. Now we'll do the problem. Calculate lambda max for this particular compound. Okay. The basic value. Here the X is hydrogen. See here. Here X is nothing but hydrogen. If hydrogen is there, basic value will be 250 nanometer. Para alkyl substituent. At the para position of the benzene ring, alkyl group is present. So para alkyl substituent, the value will be 10 nanometer. So we are adding both the values. So we will get lambda max value for the above compound is 260 nanometer. Next problem we'll see, calculate lambda max for this particular compound. Okay. Here the basic value. X is the alkyl group. See here. X is the alkyl group. So the basic value for the alkyl group is 246 nanometer. Para bromo substituent, at the para position of the benzene ring, Br substituent is attached. Okay. So para bromo substituent means the value will be plus 15 nanometer. Now you are adding both the values. So you will get the lambda max value for the above compound is 261 nanometer. With this, we have completed which unit? Fourth unit, fourth chapter. Thank you for listening my lecture.